Hi, okay, now we will see how to write the transfer function of few more magnitude plots of the Bode plot. So this is a Bode plot magnitude plot given. So we are supposed to find the open loop transfer function. So let us write GFS into HFS is the open loop transfer function. Let us write it in the form of course, let us start with K. Since we have the initial slope is negative, has to be due to a pole at the origin. So let me write it as S in the denominator. Then you can see the slope which was minus 20 dB has becoming 0 dB per decade. So naturally there should be a 0 at 2 radian per second. So I will write it as 1 plus S by 2. So this is corresponding to this change in slope, and if you can see here at 4 radian per second the slope further increases to plus 20 dB per decade from 0. So naturally there should be one more 0 at 4 radian per second. So I will write the corresponding term as 1 plus S by 4, and then at 8 radian per second I have a reduction in the slope from plus 20 to plus 20 dB per decade to 0 dB per decade. So naturally there should be a pole at 8. So I can write 1 plus S by 8, and then there is a reduction in slope from 0 to minus 20 dB per decade at 24, meaning there is a pole at 24 radian per second, S by 24, and the slope further decreases from minus 20 dB per decade to minus 40 dB per decade at 36 radian per second, meaning that there is one more pole at 36 radian. So we have 4 poles at appropriate positions, and then we have 2 zeros as per the change in the slope. So in order to find out what is the value of K, that is system gain, you can see there is a reference dotted line is given, and you can see this is in order to know the value of K, we are supposed to have some clue of what is the magnitude at any particular point. Suppose we extend this minus 20 dB per decade line downwards, so it is touching 0 dB. It is touching 0 dB line at 8 radian per second. So meaning that if you just go back by 1 octave, when I say 1 octave, you reduce the frequency by 2 times. If this is 0 dB, since the slope is equal to minus 6 dB per, sorry, minus 20 dB per decade is nothing but minus 6 dB per octave, minus 6 dB per octave. So it is minus 6 dB per octave when you're going to a higher frequency. When you actually go for a lower frequency, if this is 0 dB, then the slope is minus 6 dB per decade, means here it should be 6 dB. And then this is because you went by 1 octave back. 1 octave back means you reduce the frequency by 2 times. If you further reduce the frequency by another 2 times, the magnitude will be, here it is actually 12 dB. So at 1 radian per second it is actually another 6 dB up. Now it is equal to 18 dB. So naturally, so at a frequency omega equal to 1 radian per second, even though no information of this 18 is given, because this dotted line is given and the slope is given, we can certainly estimate the magnitude at 1 radian per second as 18 dB. So I can write it as, so magnitude of GFS into HFS is equal to 18 dB. So with this, so at 1 omega is equal to 1 radian per second, the terms that are contributing are this K and 1 over S. So that is K and 1 over S are the terms that are contributing. I can write 18 dB is equal to 20 log K minus of 20 log of omega. So since omega is equal to 1 radian per second, I can write 18 is equal to 20 log K minus 20 log 1. Therefore I can write, of course this will go to be 0. I can write K is equal to 10 to the power of 18 by 20, which comes out to be, I can find out, it is 10 to the power of 18 by 20, so it comes out to be 7.94 is the value of K. So I can just write the overall transfer function of is 7.94 into 1 plus s by 2, 1 plus s by 4, then you have a pole at the origin, 1 plus s by 8, 1 plus s by 24, and 1 plus s by 36. So this is a open loop transfer function for this magnitude plot. Let us try to do it for this particular transfer function. Suppose if you start drawing it for this, so we have an initial slope of minus 20 dB per decade. So naturally the term that we're going to contribute will be, if I start GFS into HFS, then it's equal to k by s. The slope actually increases from minus 20 to 0 dB per decade. So at 1 radian per second, actually there should be a 0 at 1 radian per second. The slope reduces from 0 dB per decade to minus 40 dB per decade at 10 radian per second. So there should be a repeating poles at 10 radian per second. I can write it as 1 plus s by 10 whole square. Why it is whole square means because from 0 dB per decade the slope is immediately changing to minus 40 dB per decade, meaning there should be 2 poles at 10 radian per second. So that's why it is 2 poles here. And of course since this is 12 is given, we can easily find out what is the value of k now. That is, at omega is equal to 1 radian per second, magnitude is 12 dB. The terms that are contributing are k and s. Then I can write 12 is equal to 20 log k minus of 20 log omega. Since this omega is equal to 1, this particular value, I can write, of course this tends to 0, then I can write 12 dB is equal to 20 log k, or k can be written as 10 to the power of 12 by 20. So I can find out the value of k now. The value of k is now 10 to the power of 12 by 20. So it is now 3.98. So here you substitute the value of k as 3.98. So this becomes a transfer function. So this is straightforward, and we are asked to find the value of omega g, that is gain omega gc. Let me say it as gain crossover frequency. One way is you can certainly use the terms that are contributing at this omega gc. If you can see omega gc, at omega gc all the terms are contributing. I can say 0 dB is equal to 20 log k, which is 3.98, minus 20 log omega gc plus 20 log omega gc. This is due to the 0, which is at 1, and then we have one more, of course 2 more poles set. I will write it as minus 20 into 2 log of omega gc. Suppose if you find out this, we'll get the value of omega gc. Otherwise, if you can clearly see here, this is at 12 dB. This is at 12 dB, and over here it is 0 dB per 0 dB magnitude. So we know that this is minus 40 dB per decade, or I can write it as minus 12 dB per octave. Since it is minus 12 dB per octave, so the frequency at this point, since the magnitude is reducing from 12 to 0, which is at a rate of minus 12 dB per octave, naturally this frequency has to be twice of this. So by graphical observation itself, you can say omega gc is equal to not 12, it is actually 20. That is 2 times 10, it is 20 radian per second. So let us try to find out using the equation what we already know. So using the equation also, we have to get the same value of omega gc, which is 20 radian per second. I hope you are clear with why it is 20 by graphical itself, because the slope is minus 12 dB per octave. At this point you have 12, at this point you have 0 dB as the magnitude. So since the slope is minus 12 dB per octave, from 12 it comes to 0 dB. There's a drop of 12 dB per octave. Octave means 10 into 2 is 20. So that's why omega GC is 20 by observation. So using calculation also you can get it. So what I'll do, of course, these two will go off. These two will go off because it is plus minus. This is 3.98. Let us try to find out. It is 0 alpha equals 20 log of 3.98 minus of 40 log of alpha a. Let me just shift cal. So I'm just trying to find what is alpha a is. You can see it is 16.96. So it is very close to 16 point. It is very close to 20 radian per second, which is it is 16.69 radian per second. So this is the value of omega GC. So you can see this is the value for the gain crossover frequency. So this way you can able to one thing, okay, sorry, one mistake I have done. So because here this is the pole is at which point? Pole is actually at 10 radian per second. I have to make this divide by 10. So this is omega GC by 10. So let me just slightly change the term here. It is not just alpha a, so it should be alpha a divided by 10 because I have the repeating poles at 10 radian per second, so I have to substitute it as omega GC by 10. If I do now shift cal twice, I should get close to 20, because here this is 20 means, oh, just a minute, I think I made something wrong here. It is just a minute, it is 0 alpha equals 20 log of 3.98 minus 40 log of alpha, or 0.1 alpha a, close, shift cal. I'm trying to find the value of, you can see it is 19.994. so omega GC is 19.94 radian per second even. Using calculation, using graphical method also, it is 20 radian per second. Here it is 19.94. So both are same. Okay, let us try to find out what is this now here. So over here for the third problem, if we can find what is, so I have the initial slope as plus 20 dB per decade, so then GFS into HFS. So plus 20 is due to a pole at the origin, it is K into S, and you can see we don't know what is this frequency, but this hint is given. You can see this is 0 dB and this is 20 dB and the slope is 20 dB per decade. Since the gain is increasing by 20 dB, the frequency has to increase by 1 decade, because this is the slope that is given. This is 0 dB, this is 20 dB, means okay, it is increasing at a rate of 20 dB per decade. There is an increment of 20 dB. The change in frequency has to be 10 times. So since it is 1, this has to be 10 radian per second. So there is a pole at 10 radian per second. So this frequency which is not given is now, of course, has to be found out by using this slope and these magnitudes. So I can write it as 1 plus s by 10, s plus 10. And then here also we have been given this as 500 and the slope is minus 20 per decade. I need to go 1 decade back. What do you mean by 1 decade back? It is 50 dB. Sorry, it is 10 times less. So 10 times less compared to 500 is actually 50. So I can write it as 1 plus s by 50. That means there is an initial 0 at origin. There is a pole at this is actually 10, and there is one more pole at there is a pole at 50 radian per second. There is a pole at 50 radian per second. Now if you want to find the value of k now, so either you can use this or this. So what I'll do is I'll just take it as I can take 0 dB at omega is equal to 1 radian per second, magnitude is 0 dB, and the terms contributing are k and s. So it is 20 log k plus of 20 log omega. So since omega is equal to 1, this goes to be 0, then k is equal to 10 to the power of 0 by 20 has to be 1. So the k value is actually 1. You can also find the other way. At omega is equal to 10 radian per second, what is the magnitude? Magnitude is 20 dB. So what are the terms that are contributing at 10 radian per second? It is still now k and s, because the contribution of this term will start after 10 radian per second. At 10 radian per second, it's again these two are the terms which are contributing. So now you can say it is 20 is equal to 20 log k plus of 20 log of 10. 20 log of, why it is 10 means because omega is equal to 10. Suppose if you substitute now, it is 20 is equal to 20 log k plus 20, this will go off, and you again end up with k is equal to 1. Whether you take this magnitude or this magnitude, the corresponding frequencies if you take, you get the same value of k. K is equal to 1 here, k is equal to 1. Either you take it at 1 radian per second or 10 radian per second. You just take it at any point. Even if you take it at 50, if you find out, the k value again comes out to be 1 radian per second. Okay, this is about this particular third problem. If you look at the fourth problem, and try to find out what is the value of just a minute. So let us find what is this transfer function. So if you can see, the initial slope is minus 20 dB per decade. So you can write GFS into HFS as equal to K by S, and there is a change in slope from minus 20 to minus 40 dB per decade at 100. So naturally there should be a pole. I can write it as 1 plus S by 100. And then you can see there is one more change in slope from minus 40 to minus 80. So there should be a repeating poles at 1000. I can write it as 1 plus S by 1000 whole square. This is repeating poles because slope is changing by minus 40 dB. So now I can write what is the value of k. So I know that at omega is equal to 10 radian per second, magnitude is 40 dB. The terms contributing are k and 1 over s. So I can write 40 is equal to 20 log k minus of 20 log of 10, because at 10 it is 40 dB. So then this becomes 40 is equal to 20 log k minus 20. So this becomes 60 is equal to 20 log of k. Therefore k is equal to 10 to the power of 3, which is 1000. The k value is actually 1000. So for this particular problem, the value of k is equal to 1000. If you are asked to find what is this gain crossover frequency at 0 dB, which you can find now. So to find this gain crossover frequency, we have to consider only those terms which are responsible at this particular frequency. At this frequency, we have terms this k, 1 over s, and these are the only three terms that are contributing. So this term, whatever that is 1 plus s by 1000 whole square, is contributing after omega g. So to find omega g here, so at omega g, so we have terms k, 1 over s, 1 over 1 plus s by 100. Only these are the terms that are contributing. So how do we write then how do we find the value of omega g? So I know that magnitude is 0 dB is equal to 20 log of, what is k value? It was found out to be 1000 minus 20 log of omega minus 20 log of omega by 100. So these are the values. Of course, so if these are the values, how do I find? So let me use the calculator to get this value of omega g. That is omega g now. I can find out it is 0 alpha equals 20 log of 1000 minus 20 log of alpha a minus 20 log of, how much is this? It's actually 0.01 alpha a. 0.01 alpha a. If you shift cal twice, you'll get the omega gc. Has to be between 100 and 1000. You can see it is 316.22 radian per second. So the transfer function now is, okay, this is 1000 by s into 1 plus s by 100 and 1 plus s by 1000 whole square. So this way we can able to find the transfer function of any given magnitude plot of a system.